Thank you. So, happy Wednesday. So I'm here to talk about embedded security, so device security. This is the security of basically processing that's designed to accomplish electrical, mechanical, or data processing. Another way to think about it is electronics in a box. This talk is for folks that are building products. This talk is for people that are procuring products, so you kind of know what to ask for. And then lastly, it's for folks that are consulting with either of those folks. There is a lot of good work. Some of the mitigations I'll be talking about are in products that asset owners have today. Some's not. There's some things I'm going to talk about that's a little controversial. I'll mention those. And there's some areas where folks aren't doing some things, and I'll point those out as well. There's also good guidance available. NIST is always a good place to start, and there's other rubrics as well, but I always find NIST kind of the best place to start. But it also is incomplete, and I'll kind of talk to that a little bit. So my background, I've been in the utility sector for about 14 years, and when I worked on DA and SCADA comms, also smart meters. And so there were events in the smart grid space that led to a decent amount of investment from the vendors and requirements from the asset owners to the vendors. One of those was in 2010. There was a black hat demonstration by Mike Davis where he created a worm that showed software going from one meter to another meter. And at that time, correlated this, there's a public event, and there was a decent amount of investment in a lot of mitigations. So it's a good example of you see an attack, then you see the investment. And so what I'm going to talk through is just some of the controls you saw. Now this is the classics, right? So in a lot of the vendors from that point forward in that space had product security governance. So basic product security requirements, basic lifecycle controls, things like focused design reviews, focused reviews on the source code, focused on security, SAST and DAST testing, pen testing, internal, external, and then incident response, emergency response, all the kinds of things you expect to see. So while I'm talking about controls, I did want to start there because really that usually is ground zero for having security in your products, is having a basic governance program. So if you're building a product, obviously that's, and most of the vendors in this space, I think we're pretty well past this stage, but not completely. Another thing you see pretty commonly now, but not everywhere, is flash encryption. And so one of the things that would have kind of slowed the precursor to attack with what Mike was doing was having the flash encrypted. Pretty much any pen test you run these days, if you don't have your flash encrypted, that's going to be finding number one typically. There's a lot of ways to do this. They're not consistent. Different chip vendors have some hardware mechanisms. They're not consistent, but there are mechanisms there, and it's complicated. One of the interesting parts is the unused flash in your device. So there was, it's probably about 15 years ago, there was this attack where people took a microcontroller and they put it in a microwave for like 7 seconds. And about 1 out of 10 of these chips, when you pulled it out, it would dump its memory out a serial port. And what had happened was the processor had glitched to a piece of code that was a manufacturing test that was doing a read of all the internal memory. And it would just kind of hardwire into this glitch when the processor got damaged. So one thing, in addition to flash encryption, your unused flash, fill it with something useful. Like if it goes to that unused flash, maybe it goes to a jump somewhere that says, hey, let me record this event. Possibly I've been glitched. Maybe I have a quality problem. That would have mitigated that really, really nicely. And the other thing I'll mention there, I built one of those types of controls at a semiconductor. I was working on a secure microcontroller, and what I did is I had the processor effectively put itself in a rock state. Said, oh, I think I'm being attacked. Let me just shut everything down. It's going to be completely non-operational. And I had somebody from a 3-letter acronym, a government agency, review what I was doing, and they go, Steve, every junior designer that's building product does this, which is tries to shut everything down when you think you're being attacked. You got to maintain your operational goals, which is perfect for an ICSOT product, right? Maintain your operational goals. And the story he explained was he had built something similar. He'd done the exact same mistake, and the device that he had built was just for some comms on telephones, securing comms, but somebody had taken that to secure comms on an airplane. and at high altitudes, bits will flip, ones will become zeros. Solar radiation will change the state of flash. And his device thought it was being attacked, shut down all the comms, and the plane crashed. So anyhow, don't crash the plane. That's really the thing I want to say. Now, the other one is signed firmware. This is, you'd think it'd be common, but it's not. So for devices that are out there, firmware should be signed. You should validate the firmware before it gets loaded, validate the firmware before you update it. And kind of the interesting thing here, there is no common rubric for how we sign firmware. Probably something to be nice kind of after the talk. Would love to talk to folks about trying to get together about finding some more common ways that we can have a more of a standard approach to how we're signing firmware. It is kind of all over the map right now. And there's good practices, bad practices. Also, people calling things signed that are really hashes. It's sort of just a common rubric. Now, here's one we'll get into where it's maybe a little controversial. So you've got test code. Test code's running in your embedded device. Disabling that test code is kind of the common guidance. If you're on a pen test, they'll say, oh, we found the test code, make sure you disable it. And so you'll have some mechanism there that says, okay, when the test code's there, make sure it doesn't run. That's okay, but really, best practice is just remove it. In the production software itself, and the reason it's controversial, there's always some part of a product organization wants to maintain that test code just in case there's a field return, just in case. Really, get rid of it. I mean, I've lived this over and over again in a variety of fields. Those use cases are generally overstated, and removing the test code is almost always the right way to go. And what's cool about that, we show up security, hey, make this more secure. We actually have saved some flash. So we get to show up as security and make things less complex, make things less flash, could even be lower cost. Here's another one that also has got a little bit of a controversial piece to it. So we are all familiar with JTAGs, I believe. So JTAGs is this test port that allows you to do whatever you want on a processor. It's there for debugging. It's there for developing a product. So what the chip vendors have done is added in a mechanism that disables the pins, and usually there's a fuse that gets blown or there's a password that's there, and with the password you can unlock it, which is another problem. Often there's a way to glitch around the protection. Even with the fuse mechanisms, there's some research on ways around some of the fuse mechanisms. All the chip vendors seem to do this differently, and in reality, there was a time when you could get a processor that had a JTAG and one that did not. And in some of the secure microcontrollers, you'll see where the JTAG logic is completely removed. So what's nice about that is, and you'll see on here, I made a mistake. It should be pin for pin compatible. You want to have all the same pins in all the same places. And that's really not that hard to do as a chip vendor. And what you'll do is have less gates, which means less real estate on the chip. So when you're putting chips on a wafer, you can get more chips on a wafer. So less complexity, better quality, ultimately lower cost to produce. So again, a security mechanism that's lower cost. When do we ever get to say that? And so this one, not just about disabling it. Long term, we really need to be pushing our chip suppliers to give us chips that have an option with the JTAG removed. And if we're procuring devices, ask for devices where there is no JTAG. It's not required. There's ways to load code. There's ways to do. Certainly, there was a time when we did this without JTAGs. Now, just an interesting point here. Some of the new parts are starting to allow remote JTAG capabilities through Ethernet or even over the internet. So the move's actually going in the opposite of what I'm recommending here. Device software inventories. I think we're all pretty comfortable with this. Certainly in certain regulatory environments, this is now hard requirement, where you have an inventory of, it was always kind of aimed at open source, but of course you want to know all the software that's running in an embedded device. What's in this box? What's running? What version's running? Does it have known vulnerabilities? Do we need to update it? Everybody's pretty comfortable with that part. It's the one below I think folks really need to pay attention to. So the processors, the devices that you're procuring have open source VHDL in them. So AES VHDL is very common in a lot of the processors. Open source JTAG. So, and again, same questions we ask on the open source software, we need to be asking on what is the VHDL components that are open source, what are the EULAs on it, and are there known vulnerabilities on the open source that's in the processor that I'm procuring? And again, that flows through all the way through the supply chain. Attack trees. So short amount of time, so I won't spend a lot of time on this. About 10 years ago, one of the folks here at the conference and I built a series of attack trees for doing some pen testing. I built them out further after we worked on this together. And this one was about disabling something called a takeout, which is a bridge between two types of communication technology. And it had a much larger fishbone-looking diagram, but basically we had kind of, right here I just narrowed it down to two ways we were looking at. If you were going to disable the RF, you might remove the antenna, and you can see we rated it by attack scale, repeatability, and cost, and then have a kind of feasibility score at the bottom. And on the right, we did, you can do remote configuration, brute force the password. You can see we'd scored the feasibility much higher, obviously, if you're just taking the antenna off. Now, it's always interesting when reality kicks in. So, a few years ago, there was an employee at one of the vendors who was fired. And when he was fired, his equipment was not taken away. And the individual logged in to a series of takeouts all across the Northeast and was changing the RF characteristics of the takeouts, was modifying the login screen to have a bunch of Pink Floyd lyrics on it, and then changed the password to something profane. Now, the net result was the infrastructure that was interacting with the water systems wasn't working. You couldn't communicate for months. Now, the FBI got involved. They found the IP address of what was connecting to these devices and found it was registered with the vendor, and very quickly figured out who it was. They bring the individual in, and they said, "So you're a master hacker?" And he's, "I'm not a master hacker. They just never took away my equipment." And so this is a good example of insider threat. So I spent a lot of years in retail and banking, and something we were very comfortable with there, and it seems like we're not as comfortable with it in the OT/ICS space, was just this idea that the insider is the attacker. We used to talk about it all the time. Imagine you're the attacker. Imagine you're the one designing the controls, that you're the one that's going to be attacking it. How do you design it in a way? It doesn't mean it's perfect if you can't imagine a way to attack it, but it's the right way to think about it. And having mitigating, compensating controls for those of us that are doing the building of these systems to protect them. And so that's one kind of from the banking side of the world. Now, the reason we saw that is in the banking system, it's very common for people, insiders, to the money motivation was very high. So you did see that happen a lot, unfortunately. And it was kind of hard to figure out who was. So anyhow, you're building an embedded device. You still need to think about identity management. You still need to think about, how do I revoke privileges, what privileges, who has access to what, why. All the same things we think about in other systems. On embedded devices, a lot of times when we're designing them, when we're procuring them, when we're installing them, this seems to get left out a lot on embedded devices. Same thing with removing the remote and local debugging capabilities. Basically, there needs to be a mechanism where that's managed when you're building the device, and then also, again, when you're installing it and configuring it. Field tool security. So there was a field tool that allowed this individual to set up, maintain these takeouts. There's all kinds of ways to do this. They also are not, there's no commonly agreed way to do this. It'd be a good thing, I think, if we shared more of the mechanisms that are there and coordinated better on this one specifically. So another attack tree, mass disconnect. So this one's about metering. And it was one when I was working in this space, worried me a lot. Was as we're building these products, how do you ensure that somebody can't run a disconnect that takes out a sizable portion of the power grid? And so you can see on the attack tree, you could have a broadcast service disconnect, and there's mitigations in place for that. And to accomplish that, you'd want to compromise the HES. Now, we had this as not that feasible, you'll see. Meter virus, this is basically the Mike Davis presentation from the beginning of the presentation. And again, had that one less feasible due to a lot of the compensating controls that were there. Well, this did happen. Happened about 2 years ago. In 2020, there was a command sent out to disconnect power at 1.23 million meters at a major metropolitan area in India. And so what happened was the system, it was a cellular-based comm system. The queues apparently couldn't, were going so slow that after an hour, only 150,000 disconnects had been sent out. The asset operators were able to shut it down at that point, but it took a while to reset the system. It took days for some people to get their power restored. It was a major event for this utility. The executives at the utility, it had an impact on careers. There was a government inquiry. Whether it was an external threat actor or an internal issue, still not public, the results of that were basically that they said they weren't going to go public with what the actual root cause was. So kind of a good example where got mitigations, it still happened. And so back to the device side of things, one of the things that helps is cryptography. Cryptography is a deep subject. Obviously, we're not going to cover this in 25 minutes related to embedded devices. But generally, encryption is for privacy. I think most of us know that. And really, in the case of a mass disconnect, not really helpful. But when you're talking, depending on the use case, it does have a place. Secure hashing is for integrity. Well, so is integrity checks off of different types of AES counter modes. And there's lots of other ways to do integrity, lots of different modes that manage this. A lot of times we'll look at NIST recommendations and we'll manage all that, but it becomes a very complicated topic on the application of the cryptography. And then the last one that I've got just as a quick survey on embedded systems in cryptography is around signatures, which is about identifying where proof of origin, where something came from, non-repudiation. Having said all that, there's other types of cryptography like homomorphic encryption. Of course, there's a lot of talk these days on quantum resistant, and really the recommendation I would have, and I just don't see enough people do this, is hire cryptographers. If you're building a device, there are cryptographic libraries that you can procure and they'll come with services from the cryptographic community. It's a complicated topic. When I was doing semiconductors, I had a team that I was working with and that was working for me of cryptographers, and even within that community, there's specialization, and it's very easy to get this wrong. And so that's one. And now, architect your certificate issuance and updating. This is something that's commonly not really thought through. And really, the basic control here is architect it, design it, know where the certificates are coming from, know the mechanism for the updates. If you're using, it's very common in embedded devices to have certificates that don't expire for identity. So is there operational certificates? How are those issued, managed, maintained? This one's controversial, and this came from my experience in the payment world. So in the payment world, if you're PIN pads, ATMs, what we would do is there was a key injection process that required a cage. It required multi-person authentication. Often had man traps involved. So a proper way to do key injection, and it cost money. Usually it was sizable. So per device. And so you're changing the manufacturing flow. I've seen it done where the subcons have to do it, and there's going to be a cost associated with it if it's done right. So if somebody's injecting keys or even injecting certs and there's not a cost associated with it, probably means some shortcuts are being taken on the key injection. So if needed, though, and I talked to one of the folks here who works on some of the OT assets, and they're doing this, which is really good to hear, which is if needed, you can inject on chip on reel, or you can inject on chip on the cartridge, which means before it goes to the subcon, there are these secure facilities that are set up to do this. This would be the right way to do it. Again, there's a cost associated with this, but there should be if it's done right. That's really the recommendation on this one. And the last things in terms of recommended controls is understand your random number generation. So if one is generating entropy, if you're doing it right, you have to run long statistical tests. There's a handful of tests recommended by NIST. There's die-hard tests. There's all kinds of different test suites out there from BSI and others that allow you to determine, yes, I have good entropy. What is the entropy strength of what I'm doing here? And what happens is a lot of times people will build a random number generator. They might do the statistical tests during development, and then in the actual product, they don't keep the tests. One of the ways to know that you don't have a good TRNG is it doesn't take a long time to get entropy because they're not running the statistical test. Why? When you have the device, and if a device is generating entropy through a TRNG, it should run those long-run statistical tests every time you ask for entropy. It should take a minute every time you ask for good entropy. If it's not, if the entropy comes back right away, it's not an actual TRNG. The work isn't being done properly. And why is that done that way? For bias. So if somebody takes the top off the part, shines light on it, if there's RF interference, maybe the random number generation acts differently at different temperatures, those biases can be detected with the statistical test. Without that, you're not going to have it. Now, Short of it is, hire cryptographers. They know entropy too, by the way. Very helpful there. So with that, I've got 5 minutes left, and again, there's a lot of good people doing a lot of good work in this space, and I do want to make sure that a lot of the controls I've mentioned here are in a lot of the devices that you're procuring today. So I'll pause for questions. I got 5 minutes for questions.
Thank you. A lot of interesting techniques. One of the concern I have is some of the techniques you mentioned is difficult to implement in a resource-constrained industrial device and also industrial IoT devices, including some of the cryptographic techniques, plus even the embedded devices haven't even implemented at large scale the identity management framework itself, right? So how do you address that? And particularly, cost implication is very concerned for these vendors to compete in the market. So just if you could wrap around, address those concerns.
So every field I've entered, whether it was banking, whether it was retail, when I was doing semiconductor, and then also in the grid space when I was doing DA and SCADA comms, this concern comes up. And I've been doing crypto on 8-bit micros running 2 megahertz in resource-constrained devices, inductively powered devices. There's a way to get there. That argument's dated. I mean, just to be blunt, it's just really dated. So back to the hire cryptographers. So what I highly recommend is make sure you engage with some of the folks that do cryptography. You don't have to have dedicated security micros to do this stuff. You can use it with general purpose micros. There's lots of techniques out there that allow you to run it in deeply. In the early to mid 90s, I was working on digital cache on 8-bit micros with 16K of RAM, and we were doing cryptography, including public key crypto. So there's a way to get there. And the other part of it is latency, right? So, and it's not that latency is very important in OT systems. It needs to be architected. I think that's the other half of it. But I don't think saying I have a resource-constrained device, therefore I don't need to do crypto, I don't think that argument washes anymore. Go ahead.
This may be just asking you to pontificate a bit, but when you talked about the prevalence of encrypted flash versus the less prevalence of signed firmware, do you think that's just because the economic, like the IP protection is understood for encrypting what's there, but signing is not important for protecting the business value? Is that why that?
So it is. So this is speculation, right? And what I would say is, for encrypting flash, some of the parts come with a bit. You flip a bit and you have encrypted flash. So that's really easy, right? Second, sadly, a lot of programmers are confident I can implement cryptography, and they'll implement AES or some type of cryptography, and often they'll implement it wrong, by the way, and they'll pick a mode that doesn't make sense for flash encryption, but they'll do it. And so I would say just the technical barrier to entry to encrypting flash is much smaller than for signed firmware. The other thing that's interesting about signed firmware, I don't know of any two vendors doing it the same way. So really kind of and Michael's nodding his head violently yes right here in front of me, which is awesome. Which is probably Michael, myself, and a few others at the next Beer ISAC, we should probably start sketching out a common way for folks to sign firmware, because there should just be, here's the cookbook, here's how you do it. Here's a classic example. Does the manufacturer of the firmware sign the firmware, or does the asset owner sign the firmware? You see that answered differently depending on vendor type. And what's the right answer? Probably us as a community should figure that out, right? And Mike's got a great answer, which is both. So I've got time, I think, for one more question, just to make sure. Okay, yeah, go ahead.
I just wanted to add a point regarding, there's a work by NIST, and I'm from MITRE. So MITRE and NIST has worked on a trusted Internet of Things device networking, layer onboarding, and lifecycle management publication.
Sure.
That actually addresses some of these.
It addresses some of them.
Yeah.
It addresses some of them. And I would argue, if you look at that guidance, if you look at the NIST IoT guidance, if you look at the 7628 guidance from NIST, which a lot of people in the room worked on, it's incomplete. All of it's incomplete.
Yes, it is.
Yeah.
It is a good starting point, but at least that is recently done. And even we are proposing some additional work on that, taking from a network layer to the application side, including that signing process and all those stuff. So I'm saying work is in the public domain is starting to come. Of course, more comments and inputs are required from the audience, and I think there's lack of that participation from the community of interest.
Yeah.
Just wanted to share that.
No, it sounds good. And yeah, probably join Michael and I a little later. That'd be my recommendation there. So I'm out of time. Very much appreciate you taking time to let me talk to you about embedded security.